We're talking to Dr. Robert Hall, one of the best-known physicists in the world. Is that a fair statement?
You stretch it quite a bit.
Well, you are renowned for three things, you were telling me. Can you put it in layman's terms? What are those three things?
Well, the first one was a power rectifier device, which I invented, the first of a kind made of germanium, and figured out how it worked, and this produced a very valuable bit of information about recombination of electrons and holes, which gave me a lot of credit as far as theoretical understanding. But these kinds of rectifiers were developed and changed into silicon form, and they're widely used now in power delivery, running locomotives, running power distribution systems and DC transmission lines. A lot of motor controls use these now in the silicon form.
And what's number two?
Number two was the laser that we talked about. And number three was a high purity project I did because I had heard that the nuclear physics community was in distress because they couldn't get their hands on lithium drifted detectors to do their studies of gamma radiation. Now I can elaborate on those if you want.
This was your success in purifying germanium, was it?
We had to carry the purification a great deal farther. In fact, we had to make it better than a millionth of a part per million with regard to almost all impurities. So this is an unprecedented level of purity. In fact, we were able to reach this level of purification and made detectors called intrinsic detectors or hyper-pure germanium detectors. It really worked, and this process is now used worldwide by the nuclear physics industry, and a lot of them are flying around in satellites, and they're all through the laboratories in the intrinsic germanium form, high-purity, hyper-pure germanium forms.
What do you mean by a detector?
Well, if you take a PN junction and you put a reverse bias on it, there's a space charge layer that will catch any ionized particles in it and give you a pulse of current. If a gamma ray comes in and is absorbed, it makes a pulse of electricity that tells you the energy of the gamma ray that came in. Now, the nuclear physics people found that they could, by using what's called a lithium drift process, they could make junctions with a space charge layer a centimeter thick. And they were making these great big detectors by a fancy process called lithium drift. And this is a fancy thing that was actually discovered by Eric Pell in the room next to me at the GE Research Lab. So I was kind of in on the discovery, and I helped him figure out what was going on. But the nuclear folks figured out a way to make these great big drifted detectors, and they were just wonderful for nuclear physics. But then I was on a ski trip, and I was up on top of a mountain with a friend of mine in nuclear physics, Dave Lind, and on the way down he said, "Bob, we need help. There's something wrong with the germanium. Nobody can make detectors anymore. The nuclear physics field is just dying to get these nuclear detectors, lithium drifted detectors."
When he said any more, that seems to imply that they were working at one time?
They worked fine for a while, and something happened to the worldwide supply of germanium, and nobody can make drifted detectors anymore. It's a calamity. And he says, "You're supposed to know something about germanium. Can you figure out what's the problem and fix it?" Well, I had never heard of these detectors. I had to go back home and bone up on it, and I realized what they were doing, and I knew, all the germanium came from one hole in the ground, from Eagle Pitcher Company in Oklahoma. And they'd changed their manufacturing process, and that screwed things up.
All of the germanium came from that one spot?
All over the world, people used Eagle Pitcher germanium. And the supplier had screwed it up so that something was wrong. They couldn't make the lithium drift process work. So they were in trouble. And it was a major problem worldwide. And what I've decided was that there must be a better way to make these detectors. If you could purify the material sufficiently, you wouldn't need these drifted process. And the advantage would be that they would be stable at room temperature. The drifted detectors had to be kept at liquid nitrogen temperature all the time. So I got a contract to try to make extremely pure germanium. It had to be better than 1 part in 10 to the 13 of active impurities. That's a millionth of a part per million, less, 10 times purer than that. So it's way out of the range of ordinary experience. And one guy famous in the field, managers, said, well, that's a novel idea, but of course it's completely impractical, can't be done. It turned out it could be done. We worked hard at it. We got the germanium purified, made some detectors, and sure enough, they did work. They worked beautifully. In fact, GE even went into the production for a while of this ultra pure germanium.